Hello, can you hear me okay? Okay, this is going to be the warm-up. This isn't the intro yet or the welcome. It's the warm-up, and if you were here years ago, we had a video with SpongeBob SquarePants, but I'm thinking you guys are well beyond that. Oh, this is going to be a good audience. Okay, so you know what this is? This is a pop quiz while we wait for the rest of the folks to get here. But don't worry, it's only 5 questions, very easy. So I'm going to give you 3 options. And if you think it's number 1, you put up your thumb, number 2, or number 3, okay? All righty. This event is put on by 2 scientific societies. One of them is the SSP. Does that stand for, number 1, the Spectroscopy Society of Punxsutawney, number 2, the Special Society of Pennsylvania, or number 3, the Spectroscopy Society of Pittsburgh? What do you think? Okay. People got it. Yay, number 3 is right. No shouting from the peanut gallery. Okay, now the next one, this is a little harder. The other scientific organization is SACP. Does that stand for, number 1, the Society for Analytical Chemists of Pittsburgh, or 2, the Society of Analytical Chemists of Pittsburgh, or number 3, the American Chemical Society? What is it? It's number 1, the Society for. We have some winners over there. See, I told you that'd be harder. All righty, now your next question is, today's science demonstration is in honor and following the model of a famous scientist. Is it, number 1, Sir Isaac Newton, number 2, Albert Einstein, or number 3, Michael Faraday? Okay, 3. Somebody had 5 fingers up back there. Okay, so Michael Faraday did his lecture for young people around a specific holiday. Was it, number 1, Thanksgiving, number 2, Christmas, or number 3, Groundhog's Day? Number 2, he did his as a Christmas gift. Okay, number 4, Michael Faraday is known for his work in, number 1, biology, number 2, electrochemistry, or number 3, psychology. Yep, 2, electrochemistry. And for the folks that are just coming, you didn't miss anything. This is just our warm-up to see how good an audience we have, and woo! Okay, this is our 5th and final pop quiz question. Michael Faraday lived between the years of 1791 to 1867, or number 2, 1951 to 1967, or 1591 to 1667. What do you think? The ones have it. Woohoo! He lived between 1791 and 1867. Did anybody get all of them right? Put your hand up if you did. Whoa, I'm impressed. I'm impressed. So next, I'll do the introduction, and it will be just about Michael Faraday. And then as we get more folks in, then I'll do the welcome. And then I'll do an introduction to our demonstrator this year. So let's talk about Michael Faraday. He is still one of the most influential scientists ever. He's quoted as that. He's known for his work with electromagnetism and electrochemistry. Some of you got that right. Now, how about his education? Well, he came from a very poor family, so he didn't have an education like you folks are having. He was what you often heard as a self-made man. Since he was poor, he had to go to work at the age of 13. And he did that. He was a runner for a bookbinder in London, England. And he did so well at that, he was made an apprentice to the bookbinder. And you know what was so important? He read the books. He read the books and he learned. And he attended scientific lectures like you're doing here today. He did that on his own, and he had people also who helped him. Faraday invented the early form of the Bunsen burner, and he was really good and loved to experiment, and then he could write it up, his ideas, in real clear and real simple language. Here's one for you. Did you know that Albert Einstein kept a picture of Faraday on his study wall? I think maybe I'll get a picture of him for my study. Maybe you want to too. So not only did Faraday do his Christmas lectures at the Royal Institution in London, England, as a gift to young people for years, also, as a Christian, he often quoted a scripture when he was giving his public lectures. And here's which one it was. It was Romans, the first chapter, verse 20. And it says, "For since the creation of the world, God's invisible qualities, his eternal power, and his divine nature have been clearly seen, and understood from what has been made." We'll wait a little bit for our welcome. We still have some more folks coming in. Okay, looks pretty good. This will be a welcome, and honestly, I'm honored to welcome you folks in the name of the SACP, and I'm the co-chair for Faraday this year for SACP, and also in the name of Dr. John Williams. He's the co-chair for the SSP this year, and also welcome from PitCon. We are so glad that you're here. Students, teachers, parents, and also the folks who will be watching this as a replay in this region and beyond, maybe as far away as Tanzania. So, don't you think it's rather interesting that you're here today to learn more? You're here for a reason. One of our volunteers is a chemistry teacher today because of coming to a Faraday science demonstration. Somebody cared enough about you to make sure that you were registered and that you were escorted here. Somebody drove you here. These two scientific societies cared enough about you, and they have a worldwide impact. And so someone cared enough, they cared enough about you to schedule and to pay for this beautiful event at this beautiful Soldiers and Sailors Memorial Hall. And then we have a number of volunteers. You'll see them in the yellow shirts. And they cared enough about you to work on this for quite some time. And next, Dr. John Williams and the Kiski Science Society cared enough about you to work tirelessly to create demonstrations for you. And by the way, John's not doing this. We didn't fly him in as a paid demonstrator. He too is doing this as a volunteer. All righty, so let me look and see if he's back there. Yep, I see him. Let me introduce you then to Dr. John Williams, and then he will introduce you to his team. He went to Penn Hills High School, where he grew up. He went to Geneva College, and then he got his PhD at Duquesne University. He's been teaching and doing scientific demonstrations for over 20 years. He's been a professor at Slippery Rock and at Waynesburg University and at Mansfield University. And at present, he's teaching at the Kiski Springs Prep School. He's married. He has 4 kids from 9 to 16. He runs 5Ks. He's a coach in swimming and cross country. And he's recently put a lot of effort into the American Red Cross. He's on a disaster action team. And when there's a fire or something, after the firefighters leave, they go in and they work with the families. So I hope you enjoy this, and won't you join me in welcoming Dr. John Williams.
Good morning, everyone. I guess the mic works. We didn't check that first. Today I've come to you guys to do a little bit of a science demo. Okay, this is of course the Faraday, and thank you, Maggie, for the introduction. Today, who we have with us are 3 of my students from Kiski Prep. Okay, this is, we'll go from this side. So we got Zach, we got Noah, and we got Jack. Okay, Jack will be doing his own thing to some degree, and Noah and Zach will be with me doing things here and there. Okay, and the point of all this is to get an idea of a little bit of science that we see every day that sometimes you'll see in class, and sometimes you won't. Because when it comes right down to it, science is everywhere. You see it all the time. I know that your teachers have told you this, and frankly, there's a lot of cool stuff that you might not even see at any given time. So it should be an interesting thing, okay? And this is one of the first things that the Kiski Science Society has started out, because we need to get science out there. The point of the PitCon organization and SACP and SSP, which is what Maggie mentioned, is to get science out there to the community and actually get new scientists into the world. And that's kind of why we're here. And that's also why I have been involved with the Faraday Lecture for 20-something years now. These, which, if you look at some of the volunteers out here, they're ones wearing that yellow shirt. Some of them have been doing this for a very long time, doing science demo and bringing science to the Pittsburgh area. So, without further ado, let's actually start going. So, what we have here, so we're just gonna do a bunch of demos here today. So, what we have here is the beginning of what we wanted to present to you guys for the Faraday, okay? And this is kind of like how we came up with the ideas that we're gonna present today, okay? So we have a little video, and we'll see how it all goes.
Hey guys. All right, so we got this Faraday thing coming up. We're gonna get to do stuff on stage and everything. What we need is good ideas, okay? Need a good idea, good theme for the whole thing. What do you guys want to do?
It's gotta be science related. Good ideas.
Good grief, I need coffee for this. I'll be back. I'll get some coffee.
I say we blow stuff up.
I also want to blow stuff up.
I'll go blowing stuff up. Let's do it then, I mean.
Okay, I got my coffee. Let's try this again. So, what do you want to do?
We want to blow stuff up. Blow stuff up.
Blow stuff up.
Okay, you know what? I think we can do that. I think we can do that. Science is everywhere after all.
Okay, so this is a very common thing in every demo I've ever done, in every place I've gone. People your age, and frankly my age too, which is like 1,000 years old, I guess, always want to see explosions and things like that. So we absolutely will be doing that. But we have to tie that into a little bit more of a theme, okay? Because we can't just sit here and blow things up for an hour and a half, although that would be interesting. We'll get to that though. We will get there, we will get there, all right? So, what we're going to be starting the talk on is, there we go, okay? So, I gave the guys a task, okay? I wanted to talk about waves, okay? And when you're talking about waves, there's a lot of different avenues that you can go with, okay? Now, when you have a wave, and we have a little bit of a rope demo going on here to start, okay? When you're talking about waves, you can very easily see it whenever you extend it out in a long period. So if Noah puts a pulse into it, you can see the wave going back and forth, right? You can see it some. Now if I pull a little bit tighter, you'll be able to see it a little better. You can see it vibrating back and forth down the line, okay? So the first thing I wanted to do was I wanted to get them to give me some device that would give me a pulse wave. Okay? And a pulse wave is just a simple wave that you take and you put one big pulse through. And it'll do something. Now there's all kinds of different ways you can do this, but what they came up with was the air cannon. Okay? And that was the first thing. Now I told them, it's like, okay, this is completely up to you. So what they first came up with was they had a little bit of a prototyping method. We'll say this, a prototyping procedure on this to actually make a pulse wave that can go out. Okay, now the idea, of course, is from me to you right now is not empty space. Okay, between me and you is a lot of molecules of air. You guys all know this because if you put your hand like this, your hand can feel the air molecules as you're hitting them. They hit back and forth, and they start scattering all over the place, okay? If you get an air cannon, what you can do is you can push a bunch of air all at once. So, what we have here, in terms of the very first one here, was the very first prototype, okay? Hey, let's go with the prototype first, okay? So, we'll do the prototype first on this one, and this was the very initial prototype that they built. So, Zach, could you show it to everyone there? All right, so explain the prototyping process there.
All right, so pretty much our idea here was we got this empty Folgers can that we found in the back of Doc's Chem Lab. We found some gloves, we found some zip ties. So we put the pieces together. The point is when we pull this glove back, it causes displacement of air, so that when we let go of it and it shoots back into this initial place, it'll shoot a wave of air outside of this front part of the cannon. It should be able to put out a candle, at least it did earlier, so we can see if that works right now.
So the one thing about the scientific process that is always something that's kind of interesting is you're always going to end up having successes and failures, and you can always learn from everything. So this one was, I think, the 5th version of the prototype that we had, something along those lines. But when it came right down to it, it was a decent attempt. So we'll see how we got it here. Yay! Okay, so what you saw there was exactly what I was saying whenever I was saying, okay, wave your hand and you can feel the air. Okay, so let's get the ping pong balls rolling here. All right, so let's actually put that into a little bit more of a visual type of thing. Okay, so the guys are going to go down to the a little bit in the stage, a little bit in front of the stage here. Okay, so basically, and this again, this is just a visual representation of this. Okay, and it usually works all right. So basically, what's going on there is we have a lot of little ping pong balls here. Okay, that is your air molecules. You have the massive tennis ball. Okay, we use that for training for the freshmen. They can't always hit the racket. It's a thing. Anyway, so okay, so what we're gonna do there is just represent the puff of air going through the air. Have at it, guys. I think one got hit.
Oopsies.
Okay, so not everything works. So it works so perfectly. I swear when we practiced that, we hit right in the center and they went all over the place. Here's the point on this though, okay? What you should have seen on that one is the big ball going in, nailing all the little balls and scattering all over the world, okay? We got one. I'm pretty sure it hit at least one, okay? Sometimes that happens, okay? So, you know, it is what it is on that. All right, so from the prototype, okay? We do have a video of the process here because the videos aren't going to last forever, but we do have a couple of entertaining videos. So this was the process of prototyping that we did.
You think this is gonna work?
I don't know, dude.
You guys seen Jackson anywhere?
Yeah, I think he's lifeguarding. Why?
I wanted to go work out with him. He texted me we were gonna go work out, but it's not.
Hey guys, working the air cannon?
Yeah, we're getting ideas now.
Alright, looks like you're doing alright. Looks like I started anyway. Look, one thing you have to make sure you do, test your prototypes, okay? I don't want to see anything on stage that's not hasn't been tested, alright? Good job, guys.
Here's the plan. We're going to try to make an air cannon that's strong enough to push you into the pool. But give me 1 second. Safety first. All right, perfect. All right.
Guys, I don't think that's from point one. That's a good plan too.
Trial 2.
All right, here. Yeah, go do your little one in it. Okay, so we prototyped this for a while, and we ended up coming up with this monstrosity right here. Okay, and when it comes right down to it, we just made a larger version of the little prototype that we ended up having. Now, we only went through, I think, 2 garbage cans to actually build this thing. The first one completely obliterated itself. It was a we're going to call it a structural failure to start on that one. It was not good. On the bright side, no one was hurt. But we did learn one thing, and that was the inside of this cannon needed to be bigger than the ring on the outside, or else you could have potential projectiles heading about halfway through the crowd, which we wanted to avoid because I don't know how good you guys are catching things. So this is what we ended up doing. And so, Zach, this was mostly your project. Care to explain?
So the idea was we started off with this trash can. We wanted a bigger model of that prototype, like Doc said. So we cut out this small hole in the bottom. We have these support woods on either side. You know, plastic's pretty weak. We didn't want to shoot something and have this thing blow up. So we have a little piece of wood on either side. We have eye hooks going through it that are connected to bungee cords, and then that bungee cord is connected to a handle right here through other eye hooks, and then we have a membrane that allows for the displacement and the air to be pushed out of the front of the air cannon.
Did we have some water in there? That's fine. So one thing that we can do, no, that's fine. Yeah, I got it. So we added a little bit of dry ice to it, and theoretically, we should be able to use that dry ice. So dry ice is carbon dioxide. We'll be playing with that a little bit later, okay? But it's called carbon dioxide in solid form. So while the water in there is going to be, looks like it's going. So the water in there is going to be heating up the dry ice. Okay, dry ice, of course, is carbon dioxide, so it's going to create smoke. So theoretically, this thing should give a decent puff of air, and it should make if it works the way we practiced on this, it should make a ring out into the stands. So let's see how this all works. We may have to actually run it again. We'll see how it goes in terms of crushing the ice and actually making more surface area, but we'll see how that goes on that. So let's see how much of a puff we can get out of this. Well, knocked over my paper anyway. So, did you guys see the puff at all? Like a ring? No? All right, I say we crush up some ice and try this again.
I mean, it worked well, it held up well, so.
You got gloves?
Oh, I forgot that part.
Yeah.
I need a glove.
You got the glove and the scoop there. Here you go, bring it over here. So, the idea here was to have a nice puff of smoke coming out and to be able to at least get enough air to knock over a couple of cups or to get a puff of air out there. It looks like with the lighting and all that, that might be a little bit tricky. So maybe we'll set up a tower here to blow that around. Yeah, got the hammer. Yeah, crush it up first. There we go. All right, so thank you. So dry ice is on the cold side. But it is useful for a lot of things. All right. We'll add a little bit more water too. Aim it at the cups. We'll try to knock them off the stage. Because we are getting a decent puff of air out of it. We'll add a little bit more water in there. Yeah, we could add a little more. We have water. Yeah, it's probably a good idea. Just move this out of here. Got it aimed right?
I think so. I think we're good, yeah. All right, let's see if this works.
All right, hopefully we're going to put a nice O-ring out of it.
Ooh, it just shot it out.
You shot it out?
Yeah. Look, it's all over.
All right, so did we get a puff? A little bit one. You probably might this on this side a little bit more. All right, fair enough. All right, we'll move on from that then. We may try playing with it later if you have some time after the event. We're going to move on. That was an entertaining prototyping process, and we definitely did get a decent amount of air going through there in practice. So that's okay. Put these back over here. All right, back to waves, okay? Whenever you're talking about waves, one of the things that comes up a lot is sound waves. A puff of air going through the crowd, and the reason I wanted to start with a puff of air is because the puff of air is simply just air molecules bouncing around. Every single one of you in the crowd here probably has a phone in their pockets. Okay, the phone, yeah, everyone has them, you know. So how does the sound actually work? How does the sound get from that phone to your ear? Okay, everyone knows that you have like speakers, microphones, you're hearing my voice right now. Okay, what that is fluctuations in air, very similar to the way the air cannon goes. Now, the air cannon wasn't exactly focused, and it wasn't back and forth. But when it comes right down to it, the vibrations of almost anything can cause these fluctuations. So if I pluck a string, it's out of tune, yes, I know. So if I pluck a string on the violin, what you're gonna hear is the vibrations of that string going back and forth. It's vibrating the air molecules between my violin and your ear, and then the small membrane that is in your ear is vibrating back and forth as well in time, which is why we hear the same thing, okay? And then the little bones in the ear and stuff like that will send signals to the brain and all that good stuff, okay? But how do you change the pitch of the sound, and how do you change it in terms of how you hear something a little bit differently, depending on, okay, the E string, kind of E, the kind of A, yeah, like I said, kind of D. Okay, well, when it comes right down to it, you're hearing different, what you're hearing is different widths of these strings. Okay, and because the different widths of the strings are like, okay, one is very large, one is very small, it changes the pitch because it vibrates slower or faster. Now, anyone who's ever worked with any type of instrument knows that you have to tune them before. Okay, and the reason I didn't bother tuning this is because when you pluck it, you can hear the sound changing, okay? Well, why is that? Okay, well, when it comes down to it, rope. So when it comes right down to it, you hear that sound changing because the rope itself, or the string, is becoming more tight. So I turn the tune on the top, it becomes tighter and tighter and tighter, and because it's becoming tighter, the wave itself is changing. Okay, so if I go over here and I pluck this, okay, this is the same thing as the violin string. If I pluck it, you can see the wave going back and forth. If they both pull it tight, without breaking it, it's going faster, isn't it? And you can definitely see the wave going back. Now, if they put it real loose, it's going slower, isn't it? Okay, so the tighter you pull it, the faster it goes. Okay, but the further in they come, it'll go slower because there's not enough on it. And that's exactly how this works. Now, that's not the only part of the story. The other part of the story, of course, is the front plate of the violin, the chamber inside. What's the chamber filled of? Well, right now, air, right? Just regular air like you breathe right now and I breathe right now. You could fill this up with something, and we can do this if we wanted to, but the sound change with filling this with helium is very subtle. And I would have to actually tune the violin, and you guys will have to be basically music majors to really hear the change in pitch of helium versus nitrogen, okay, as you're doing that. Now, you can see these things, and right, so we're not going to do the hydrogen in the violin, okay, but what we can do to change that part of it, okay, has anyone ever breathed in helium? Okay, so what happens to your voice? Yeah, one of the things I like to do to my students is give them opportunities to do all kinds of stuff new, and I also like to torture them to some degree. So we're going to torture Zach a little bit here. So Zach is actually one of my prefects at Kiski. Okay, it's a boarding school, so we have students on campus, and like all the time. And I have to check in at them at night to make sure everyone's good and all that. So one of the things that we end up doing is we'll check in at night, make sure everyone's good. And some of the guys, Noah here is having a hard time sleeping. Well, I want to make sure he gets a good night's sleep. So I'll tell Zach, hey Zach, can you give him a quick, lullaby? Okay, just a quick lullaby at night, okay? Because it's nice to do, right? So usually we choose between what? You Are My Sunshine, anything Metallica, and Twinkle Twinkle, right? Pretty much. So that's pretty much what we end up doing on that. Helium? All right, okay, cool. All right, so we'll give an example of Zach singing just normally without any interference, so that way we can tell the difference here. So go ahead, take the stage.
All right, I'm gonna look up the lyrics for this poor rendition of Twinkle Twinkle Little Star. All right. Twinkle, twinkle, little star, how I wonder what you are.
Come on, really get into it here.
Up above the world so high, like a diamond in
Okay,
the
that's good,
sky.
that's good, that's good. Okay, so.
Oh, just wait, just wait.
For some reason, Noah hasn't slept in 3 years. Regardless of that, all right, so what we're gonna do is we're gonna have him breathe in some helium, and let's try it again.
Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a diamond in the sky.
Take another breath.
Twinkle, twinkle, little star, how I wonder what you are.
Okay, two big breaths of just normal air. Just normal air, normal air. Okay, try it now.
Twinkle, twinkle, little star, how I wonder what you are.
Okay, so what is going on there? Yeah, you should definitely give him an applause on that. See, and he thought all that practice I made him do in the dorm wasn't worth it. See, that's why we practice, right?
Thanks, Doc.
All right, so what's going on there, okay? So I've heard people explain this, and they're saying, okay, your vocal cords are getting tighter and stuff like that, okay? That's not happening, okay? Because if I'm tightening his vocal cords, that could cause damage to Zach, which I would not do, okay? But what is happening is the chamber, just like the violin, inside the violin, the chamber in there that actually resonates the sound, okay? So you have this chamber inside most instruments, okay? If you look inside there, okay, you have this shape, which for a lot of reasons is very important. But the chamber itself is full of air, okay? Depending on what's in there, the sound will actually travel faster or slower, depending on what's going on, okay? So right now and normally, whenever you're talking, your chamber, all your vocal cords and everything in your throat is all just full of air. If you do this with helium, okay, air is mostly nitrogen. Nitrogen, got some oxygen, carbon dioxide, all that type of stuff, right? But you're talking about a molecular weight of about 14, okay, and all the air there. If we add helium, okay, helium has a significantly less molecular weight, and therefore the sound waves could actually travel at a faster rate. So instead of going the 340-something meters per second, you're actually speeding it up, which is why you hear the pitch go up, okay? And when it comes right down to it, that's what you're seeing with Zach, and that's why whenever you do this. Now, there is another gas I will mention that will make your voice go lower. We couldn't actually get that. You can only buy it in tanks of industrial size. But that might be something for a future Faraday, that we get that one. And it makes anyone's voice go real, real, real low. Because again, you have a very heavy gas, okay? And the heavy gas will actually cause it to go down. And therefore you have the rope, which is going looser, and well, not looser in terms of that, but the chamber, the rope doesn't change on this one. It's just because the air is different, the sound waves are going at a different speed. Okay, so, twinkle, twinkle. All right, so back to the rope one more time. So we're gonna get set up for the Rubens tube here. Okay, so Jack, if you could hold on the rope there for me. So, when you're talking about sound waves, okay, obviously a pulse wave is what I wanted to start with, but that's not what I wanted to actually end with on the sound waves. So when you have a pulse, you have a single thump that's going back and forth. We'll pluck it instead, okay? Well, sound waves are far more complex than that. What you have usually is multiple things all at once, okay? Or if you set it up and you get it just right, you can actually get it so that if you look at it, at least from your perspective anyway, I'm trying to set up a standing wave. It seems to not be working for me right here. So, Zach, see if you got one earlier, yeah. All right, there you go, that's one. So if you look, a wave that is bouncing off of something else will bounce back, and you'll see that the middle part of that rope isn't really moving much, is it? Okay, if we get it right, it won't be. And so you have two nodes, and then a huge movement, and then the part in the middle isn't moving much at all. Okay, good enough? So, whenever you're doing that, you could, whenever you're doing that as in speaking, you could actually set that up so that as the echoes and all that reflect, you can hear things stronger or less strong, and you can actually see that some way. So what we're going to do here is we're actually going to set up the Rubens tube. So this right here is a Rubens tube, okay? And what this does is it will convert sound into something visual, okay? And the something visual we're using is fire, okay? So the whole thing's gonna light up, and what we're gonna do is we're gonna trap the sound wave within here, and you'll see the sound wave, and you'll see those nodes. Because when a sound is going through something like this, okay, depending on the frequency and the wavelength, you'll actually be able to see where it constructively and destructively interferes with itself. Because the air pressure is what a sound wave is. And if the air pressure is pushing more gas or less gas out of this, then you will see visually the flame, the plasma dancing around here at higher or lower pressures as it moves along. Now, a pulse wave, as it's going, just like the first thing, the air cannon, will go and it'll hit the whole thing for the most part all at once. But a more complex wave has more than just pulse waves, okay? So you'll see a lot more in terms of what's going on there. So oh yeah, we got the video, that's right. So we built this thing. I actually had Mark Hiles out of Stony Lonesome Fabricators build this for me. And when it comes right down to it, we weren't 100% sure what was going to happen the first time we lit it up. It should all work in theory, but so we have a little video on that one too. So, okay, we talked about waves a little bit. We talked about pulse waves a little bit. Yeah, I'm not necessarily a huge fan of death by PowerPoint. I just like to point this out, so. Okay, we'll go there. So we'll come back to that one later. All right, so the Rubens tube itself. Okay, so.
All right, let's test this thing. Go ahead and strike the match. All right, I'll get the gas started here.
Guys, how likely is this to go wrong?
Rubens tube shaped crater. Non-zero.
Okay, safety first this time.
Think we're ready?
Should be good. I think that's a success. All right, so without further ado, okay, so let's set this up so first thing I'm gonna do is we're gonna place something over the speaker here, and we're gonna have something with a decent pulse to it. Okay, so we'll set that up and we'll get that rolling, and you got the match over there?
Yep.
Cool, all right. You wanna light it?
Yep, I can do that.
Okay. Give you a big long stick.
Yeah, that probably go out of the way.
Yeah. Well, actually, you know what? I'm just gonna.
All right, ready?
Yep.
All right. Okay, so the chamber has to fill with a bit of gas. All right, try it. So it's filling the chamber right now. Once it fills, we'll get there. You can see it starting. There it goes. Now we're getting it. It'll get there. So there's a lot of air in there. So it takes a bit for the gas to actually get all the way over to it. But as you can see, it's slowly but surely growing. Okay, so now what we're seeing right now, yeah, close that one a bit. I'm getting a bit of a breeze. Yeah. Okay. Okay. So it looks like we're doing pretty good here. All right, so the first thing we're going to do is set up a pulse just from a song we have. Okay, so go ahead and fire that up. So, as you can see, when it thumps, just from that, the whole thing kind of dances. Okay. We'll move on to the next one, that one. Okay, I'll turn this down a little bit. Okay, so, and you can see that now. The one thing that we have about this particular auditorium is there's a little bit of cross drafts and breezes that are going through. You can kind of see it dancing right now. If it's perfectly still, it works beautifully. But one thing we did notice was that when you can set up a standing wave, when you can set up a standing wave at different frequencies, you can see it very clearly as it goes through. So Noah here, obviously is a bassist. Okay, that's it's something like a violin. Only it's much, much larger, because he had to be better than me in terms of the size of his violin there. But it works to the same principle, okay? So he's going to go and do a scale on this. And what you should see is the different notes as he plays the scale, and they should show the different waves along the Rubens tube. Okay, so I'll fire this back up a little higher. Hold on. No, okay. All right. Okay, try it one more time here. Yeah. There we go. Go ahead and pull. All right, try it now. Oh, good grief. Okay. Yeah, that's much better. Okay. So play a particular note. Okay. That I can show this. So yeah, go ahead and. All right. So look at it right there. Just keep it right there. So you can see right here you got constructive interference. The waves coming back and hitting itself, causing a higher pressure in the gas inside the tube. Whereas right here, you have a very low pressure portion. So the gas is not pushing through the tube, and you're not seeing as much. But you can also see from this, as he goes through his scale, the wavelength from here to here is changing as he goes through the scale. That's a good one there. It's it. All right. So on the base, you can do certain things on bases. Bases I've always found are very dour and all that. But so Noah did want to actually play something. I think it's a good idea to play an actual tune. Bases actually can play an actual tune too. So let's let him do that and just watch how the waves hit the Rubens tube there. Nice. We'll let that go there. Okay, so you could see the wavelengths, you could see how they interacted there with the air pressure within the Rubens tube. And we'll let this cool off a little bit. And it does end up getting a little bit toasty, that's for sure, as you have that. But yeah, you can pull it over there if you want to, yeah. So we'll get that because we're using that for later. Yeah, use the thermal gloves, yeah. No, those aren't the thermal gloves. Yeah, it's on the dry ice. Okay, so we'll move on. We'll move on as they're setting up the stage on this one for the next piece. So, all right. So, I wanted to hold on. You're caught. There you go. Okay. Okay. So, waves are not all sound. Okay, and when it comes right down to it, there's a whole lot of different types of waves out there that are not just sound waves and pulse waves and things like that. So, you good? Okay. All right, so we finally make it over to Jack here. Okay, so Jack, what have you been working on here?
Split water.
Splitting water. And how are we doing this?
Electricity.
All right, so what we're doing, you can fire this up if you want to. Yeah. So when you're talking about there's not much is going to happen over there yet. That's more of a piece we'll talk about there. So when you're talking about waves, a lot of times people will start talking about the duality between light waves and sound waves. Okay, light waves and sound waves are completely different things to some degree, but they share a lot of similarities. Okay, and one of the things that we can do with light waves is you can visually see, I mean, our eyes are amazing detectors, and you can visually see the wavelengths of the light. So what we're going to do is we're going to be messing with water, okay? Water is what? H2O, right? Everyone knows it's H2O, okay? That's the one chemical that almost everyone knows, okay, is water is H2O. Well, water is made up of one oxygen and two hydrogens. Okay, so this is a chunk of ice here, okay? So, but you have, if you look at these, okay, one oxygen, two hydrogens, okay? And they tend to gather around and all that and form a liquid or a solid or something along those lines. So what Jack is going to try to do here is he's going to end up splitting water. Now there's two reasons he wants to do that. If you split water, what do you get? Oxygen and hydrogen, right? Which are fun gases in and of themselves, okay? But when you take, so actually we'll let Jack explain this a little bit. So go ahead and explain your the pH experiment here.
So essentially what we have is potassium nitrate. It's a salt. So we have 3 beakers filled with 750 milliliters of potassium nitrate, and then we have salt bridges in these U-tubes. So these little black strips, those are carbon fiber rods. So they are going to be conducting electricity through these this copper wire right here. So when we end up adding about 5 milliliters of sodium hydroxide, it's going to start to turn pink.
Okay, so why is it turning pink? Why are your eyes seeing the pink color? Okay, well, the reason is because you are seeing the light in there, or I should say the light being filtered through that, and it is exciting and doing all kinds of things on its own, causing the wavelength of light to change. Okay, wondering what was hissing there. I was wondering if I had to worry about a tank. Okay, so, and as you can see, it's a very different color. Now, what was in there? Okay, you have an indicator in there that's actually causing it to change color. So what Jack is going to do now is he's going to start setting up the electrodes themselves, and we're going to start splitting water. When water splits, you have an anode and a cathode. Anodes attract anions, cathodes attract cations. Okay, and when you turn it on, you can fire it up if you want to. What's going to happen here is that the anodes and the cathodes are going to start splitting water both sides. Okay, one side will end up splitting the water and creating an acid. The other side will split water and create a base. And what we can do is we can use those two reactions to cause a base to form and an acid to form, and hydrogen and oxygen gas to be released by each side. Okay, and that's what we're doing. Oh, by the way, Jack, this is Soldiers and Sailors Memorial Hall. You should make this patriotic. Okay.
I'm going to need about 15 minutes.
15 minutes. All right, we'll go one more thing before that then. So what this is right here, and I'm not sure if we can get a zoom-in shot on this at all. This is the same experiment as that over there. Okay, and what you should see if you zoom in right into about right here, okay, and you might be able to see it some there, is the bubbles are forming, okay, on each side. Because what you're seeing there is water being split apart. Now, I don't have any dyes in here, but hydrogen and oxygen gas are going to be starting to collect on that or inside there, very small level amounts. But that is the exact same experiment as this. So 15 minutes, huh? Yep. All right, I guess we're just going to have to small talk for that. How's it going, Greep?
It was going good until fantasy this week. I drafted the Patriots defense, and as we know, they kind of suck. So that's how my week's been.
Oh, my goodness.
Yeah.
So we've discussed this before. Now, I understand. I grew up in Penn Hills. I've been in Pittsburgh all my life. Okay, and I've actually talked about this with the guys quite a number of times, that some things just aren't made the same way. That some things are sturdier than others. Okay, actually, we have a recording of one of those conversations, I believe, on this. Yeah, we'll get to the recording eventually here. Okay, so yeah, we can go back to lightweights.
Jeez, my fantasy's popping off this year. I wish I could say the same. Have all these Patriots players on my team.
You drafted Patriots?
Yeah. They're not built like the Steelers, man. What do you mean?
See, what do I mean? So everyone knows what this is, right? Terrible towel? See, Steelers stuff is made more sturdy. Now, this is actually with the Myron Copes terrible towels. I encourage everyone to actually, get these, because when it comes down to it, it actually supports a charity. Okay, this is what was it? It was Valley School, I believe. Allegheny Valley, that's what it is. I couldn't think of it. There's so many Valley schools around here. Allegheny Valley Schools, it's a charity that helps those less fortunate, for that. So I encourage you guys all to do that. Plus, let's face it, when you're watching a Steeler game and they do something good, doing this type of thing is just something that has to happen. But other teams have actually tried to make a similar type of thing, okay? They just can't do it the same, and I'm going to prove that to be the case. So what I want Zach here to do is to make some garbage. Okay, so he's back there and he's using his best artistic ability to make some garbage, and we'll see how this works. We're getting there. Where's that the beaker at? The beaker in the, oh, there it is. All right. So obviously, that's kind of an abomination. But here's the thing, okay? So if we take the Patriots thing here, okay? Yeah, we'll kill the lights on this one, yeah. Okay? So we have the Patriots thing, and they got the bucket of water right there, so we should be good, yeah. Yeah, so what's going to happen here? All right, let's see. So you can see it's even having trouble lighting, okay? When it comes right down to it, it can't even do that right. So it's going, it's starting to go, yeah. So we're getting there, we're getting there. So if you see that, you see it's going, it's clearly scorching, it's clearly burning, you know, there it goes, now it's going up. So this is about what you expect, right? Yeah. All right. Okay, so some of you guys, so one of the, I was discussing this particular one with a couple of people in my department, and we have one guy who's a Patriots fan, and he's like, oh, I don't like this at all. And one guy who's a Steeler fan said, no, I don't like this at all, because what we're going to do is we have to try the same thing. Okay, so, but you know what? Here's the thing. I am confident that the Steelers, so the Steelers will actually, dump it all. So the Steelers one is made of different stuff, okay? So I'm actually going to add some fuel to it, okay? Because when it comes right down to it, this made it, I mean, yeah, I mean, whenever you're the Steelers, you have to play against the refs. You have to play, I mean, you know, it's just a different type of thing. So you see there's a lot in there. So I'm going to bring this out there a little bit. So, all right, we should be good there. All right, so if this doesn't work correctly, then we can't ever show our face in Pittsburgh again. All right, let's see how we do. It's going. And you can see there's a huge difference there. Huh. Look at that. Not a scorch mark on it. Isn't that amazing? Well, hold on. Let's, we got to see both. That's just kind of the nature. Oh, look at that. It's a shame. Oh, that's, well, you know, I mean, you know, it's just the way it is sometimes, you know. All right, we'll put this back over here. Okay, so we've had a little time to pass. What do you think? Think we're good? All right, so like I said, I want to see some patriotic colors going on here. So if you zoom in on this right now and you actually take a look at it, now the blue one you can see real well here. You see, if you look in here, if you look right on the edge, and you guys can probably see it even from where you're sitting, it's actually starting to create a different color in there, okay? So you have the red on the one side that's going real nicely. You got the pink in the middle that's doing all right too, and then you have the blue. Oh, hold on. I said patriotic. Make it patriotic, man. There you go, Sirloa. So, there we go. It was working? Okay. There you go. Much more patriotic. All right, actually, no. I don't know if that's American red there, dude. Like the colors? Yeah, no. It's not bad, but I don't think it's like quite American red. You know, it doesn't quite match the flag. Yeah. We also got to get rid of it anyway. So let's turn it into water again. It's all good. Yeah. So, what are you seeing there? What you're seeing there is, think of this as a level of electrons, okay, within the molecules of the chemical in there, okay? And whenever you have a chemical, you have these chemical structures that are kind of floating around, okay? So you have something like this. The electrons are caged by certain things. Okay, certain structures and things like that. When a light beam goes in there, it's a photon, which is the same, which is a muon, the same as an electron. And what happens is the electrons can go, and I'll use my ladder here for this, different levels. Okay, so you could have a higher or lower. Now, when you have a lower level, that's about it. When you have a higher level, it's a lot more space to drop, right? So if I take this and I actually throw it from like a larger level like the stage here, and it comes down to it, the higher you go, the more energy you're going to have, and the more your sound is going to hear it. It works the same way with light. So with light, you drop that electron down from a high energy level to a low energy level, and the amount of energy in that electron drop will come out as light. Okay, there's some kind of frequency, but the visual stuff that you saw there was all about the light that's coming out of it, and you're seeing it, or being absorbed by it. Actually, it's more absorption than fluorescence type of thing. But that's what you're seeing there, and that's why different things. Now, why you see the color change is because if you change the structure and you remove a chunk or add a chunk on, the electron can go further, and if the electron can go further, it's more weakly or more tightly bound. Okay, and therefore the electron can move around less or more, and therefore you have the more energy or less energy. And again, it's just like falling off the stage or falling off a ladder step. Okay, one little thing. Okay, it's not that bad, but I'm not doing that jumping off the stage. Okay, because I don't want to hurt myself. Okay, so that's the light thing. Now, when it comes right down to it, you can obviously see light things in different ways. So I don't know if I have a slide on that. We're just not going to bother with a PowerPoint. Okay, so we've made it up to the looking at how light can be seen when these electrons fall to other or excite, fall back down, and you'll see different types of light, different wavelengths of light, which correspond to different colors. So what I want to do is I want to show you the first one, which is going to be hydrogen, okay? And what we're going to do is we're going to burn it, okay? So the balloons in the back are not just for decoration, but we actually have these here for a reason. So we're going to go through a series of different metals that we have in here. Now, the first one only has hydrogen, okay? The hydrogen itself is just going to sit here and it's going to burn, okay? And it's going to burn at the hydrogen's wavelengths, okay, as it falls around. So I'm going to put some earplugs in because this might be a little bit noisy. Thank you. So here's the first one. This will be only hydrogen in here. What's the next one, anyway? What's that? No. Do the metal series first. Yeah. Okay, so what did you see? Or more specific, what color was it? Kind of an orange, red. All right, let's see if we can change the color. Let's kill the lights up there too. We'll try to get this. Let me see. What's that? Potassium. All right, so this particular balloon is full of potassium. Okay, would you like to light it? All right, we'll take care of that. Yeah. Okay, Zach, if you would. So what was that? Kind of a blue, purple in there? Definitely a blue in there, I saw that. Now, there are multiple different levels that you could have in a single element as you're burning this. Obviously there we go. So obviously you still saw the yellow of the hydrogen because these all have hydrogen in them. But you also are now going to see the metal themselves burning as you're doing it. So what's this one?
This one should be strontium.
Okay, this is strontium. Okay, another chemical on the periodic table here. Say these are all metals. Yeah, do it. As you can see, they all want to blow things up. This is one of the things. So what do we see? Definitely a red-orange type of color. See, that one was actually so strong it overwhelmed the hydrogen. So whenever you were seeing it, the hydrogen, you could almost not see the hydrogen color at all, right? So what do you got in this one? What's it? Copper? All right, so this one's copper. What's your guesses? I see here some green, some oranges. All right, let's see what we got. I got to admit, that one is probably one of my favorites. I just love that blue-green kind of color there. And all of this is all about the wavelengths of light that are coming out when the electrons fall back down, and that light is released. Because this actually, the source of the light is the burning in the balloon and the plasma generated there. So what's this one here? Sodium? Okay, so this one here is sodium. This is table salt. Okay, when it comes right down to it, you even the most common things like table salt, you'll see a nice little explosion from, well, a color change from. So what'd you see? Yellow. Should be a nice strong yellow. There may have been a little bit of green on that, but there was a strong yellow in that one. Yeah, we do metal powders, yeah. So just because we're blowing things up anyway, there are a couple of other ones that we wanted to play with, because there are metal powders you can do, and you can burn the metal powder themselves. These are a little bit different than the first ones, because they're not necessarily a color. What's this one? Iron? Okay, so this first one is iron. Okay, so it's iron powder. Exactly, Iron City, that's exactly it. Say, this is Pittsburgh, we're all about steel and iron and all that good stuff, so. Hey, Jack, start making your thing. Keep it liquid until I tell you to put it on the papers, okay? What's that? Keep it liquid until I tell you to put it on there, yeah. Okay, whenever you're ready. All right, so what was different? Yeah, the sparks. Because you have little flecks of iron in there, what's happening is the hydrogen brings all that energy into those iron that was in very, very small, high surface area pieces, and they'll catch, okay, and they'll glow, which is why you saw a little sparkler effect there. So what's this one? Magnesium. Magnesium? All right, this one's magnesium. This one, you'll notice. It'll be bright. So, unlike the iron on this one, you have very small pieces of magnesium, and magnesium burns very bright and very hot. So, whenever it got in the air like that, it created a little dazzling little effect, whereas the iron had larger chunks, basically. It almost felt like it was larger chunks. So it's kind of, instead of a sparkler, it's a kind of like a, I don't know, fairy dust type of thing. All right, so this one's aluminum. This one should be interesting too. Create more of a cloud. All right, this is the oxidized ones. All right, so to close out this portion, okay, we're talking about, so over in Jack's thing, okay, separating water, okay? Now, you separate water, hydrogen and oxygen don't really like being by themselves. They like being in water, and it's a good thing for us, because otherwise we'd be very thirsty, okay? But when it comes right down to it, if you put hydrogen and oxygen together and add some energy, they'll form into water, okay? And it likes to be that way. So what we're going to do is we're going to have a combination of the two, and we're going to set them off. Okay, so the very first one we're doing, yeah, we're going to do pure oxygen first. So this is just oxygen, okay? And we'll start with that one. Okay, so what happened? Nothing, right? Okay, here's the reason why. When it comes down to it, when you burn something, okay, and you could ask the fire department on this, you need fuel, you need oxygen, and you need heat of some time. Now, you guys have all heard this, probably all through elementary school and everything. That's the fire triangle and all that, okay? Well, with oxygen, there's no fuel. Now, oxygen, if it's given fuel, makes a slightly more energetic type of reaction. So this one here is an imperfect mixture of oxygen and hydrogen, okay? Now, what is water again? What's the chemical formula for it? H2O, right. So if you have 2 parts hydrogen and 1 part oxygen, that would be what I'm talking about as the perfect mixture, right? This is imperfect, okay? On this one, you might want to put your fingers in your ears and stuff on these things. Yeah. Everybody ready? So that was an imperfect mixture of hydrogen and oxygen. Now, we have one that's close to a perfect mixture, okay? Now, what I want you to do when we're doing this one is to take a look at two things. One, where the fire is coming from. Because every time the other balloons, the fire was always on the outside of the balloon feeding into it, right? On this one, there's already oxygen in there. It doesn't have to wait, okay? And it wants to be water. It wants to get back together, because right now it's just not happy. So this one might be a bit loud, okay? But I also want you to take a look at the crowd as the shock wave migrates up it. Jack, you can start doing that. Wipe it on it, yeah. That was awesome, yeah. So the two things that I told you to look on, okay? One, how long did that flame last? Very quick, right? It was gone. Second, did you watch up the crowd as the shockwave hit people? Because there's so much pressure being built as that goes off that first off, you can obviously hear it. But second, it'll push all the rest of the air to you, okay? Which is also why the ping pong balls scattered around here and there are also pushed a bit that way, if you notice that. So, okay, we'll move on. Okay, so enough of the hydrogen balloons. I told Jack that the color experiments were nice, but I wanted something with a little bit more of a pop that had to do with that shock wave that you saw migrating up the crowd. Okay, because when it comes right down to it, shock waves are more like that pulse that we started with the air cannon, okay? But I needed something a little bit more energetic than the air cannon, okay? So what Jack found and what we talked about and figured out was that nitrogen triiodide is a really kind of a neat little chemical, okay? And when it comes right down to it, what he's making here, okay, is that chemical. So nitrogen triiodide has a nitrogen with 3 iodines stuck onto it. Iodine is very large. Nitrogen is very small. And frankly, they crowd out, okay? So you just don't have, it doesn't have enough space and it doesn't want to be around itself. But in a liquid form, you can't hurt it, okay? It's just gonna sit there. It'll degrade on its own. But what's more interesting is if you could actually make it degrade relatively fast. Okay, so that's what we're gonna try to do here. But like I said, it is made in liquid form and you can work with it in liquid form as he's doing right now. And if you look at it, it's kind of like this, I don't know, kind of a nasty color to it, I guess, because you got that iodine that's floating around in there and it gives that dark hue to it, okay? So if you see that, he's making that. So what we're gonna do is we're gonna put that on a couple of these little filter papers, and then, got it. I'm gonna put the filter papers up on here. And okay, so. We're running a little bit over time on this one, but that's okay. Okay, and we're gonna let that sit there a bit. Now, this is not one that I could do whenever the hydrogen balloons were going off because of obvious shockwave issues. Okay, but what we're gonna be doing there is we're gonna let that sit for a bit and let it dry out. Okay, so hopefully we'll have enough time. We have a little bit of time left, so we'll do that. So while we're doing that, I want to talk about a little bit about wave fronts and things like that. So we'll move on from that. And yeah, I'll move on to dry ice. Okay. So we have a chance to play with dry ice, and I feel like we need to do such a thing. So what we have here is a bunch of dry ice. So dry ice, and where's my glove anyway? That'll work, thank you. Yeah. So I told you I'd talk about dry ice. Let's talk about some dry ice. So this is dry ice. So this right here is carbon dioxide, okay? And I actually do have a slide or two on that, don't I?
Yes.
Unfortunately, to move the slide, I have it in my right-hand side pocket, so. All right, so, I was there, wasn't I? That's liquid nitrogen, we'll get to that. Okay, so dry ice, the cool thing about dry ice literally is that it is very cold. Okay, so this is negative 109 degrees Fahrenheit or negative 78.5 degrees Celsius, which is why I like to wear a glove, because otherwise it makes your hand really cold really fast, and it'll burn you, okay? The same way as a fire will. Okay, but that is a chunk of carbon dioxide, the same stuff that you're breathing out right now, okay? But because it's in a solid form, there's a lot of it right there, okay? So we're gonna prove that to you, because what we're gonna do is we're gonna take a chunk of dry ice, and I'll give you the glove and stuff, so you can do this. What's it? Water's right here. Yeah. So we have a bucket here that we're going to put a couple of, or put some bricks of dry ice in. So what are you hearing? So the metal itself is interacting with, this is interaction with the dry ice, and you can, all the gas being liberated will actually cause it to rock around, and you're hearing that gas being generated. Okay, no, not that stuff, use the Dawn. Yeah. Yeah. So we're gonna add a little bit of soap to it, and we're gonna add a little bit of water to it. You got a towel, don't you? Oh, I got one, okay. Well, we have some Patriots towel in there. Sorry, it's just the way it is. Got that?
You want to pour that in there?
Yeah, we'll go ahead and pour it in there. Yeah.
Need more?
So if you look inside there, you can switch it over to the camera over there. If you look inside there and see what I'm seeing there, what you're looking at, or what I'm seeing anyway, is the dry ice itself liberating all the carbon dioxide. And what we're going to do is try to capture that carbon dioxide being liberated by it. Hold on, let me help you out there.
All right.
So when it comes down to it, sometimes you just got to prime it with a little bit of soap there. All right. So yeah, it's coming out pretty quick. We do it this way. Wow, this is really just not cooperating right now, is it? Yep. Hey, not every science. This is the nice thing about science demos as opposed to like a theater thing. The science will do what science does. There's good and bad to that. That's just kind of the way it is. Never be worried about failing, because sometimes you. Oh, I had it for a second there. It was definitely showing up. You know, the funny thing is, whenever we were, let's try that one, yeah. Yeah, let's try that one, yeah. All right, well, we'll move on. We'll come back to that one. This is one of the ones that worked the best in trial, too. I hate giving up on things. Let's say you can definitely see, the air being, the carbon dioxide being generated from it, but yeah, it's just not cooperating right now. All right. Well, you know what? We'll come back to that if we get the chance to. All right. Well, what I wanted you guys to see is the gas being coming from it. Okay. Now, theoretically, the bubble should form and stick there for a bit before it explodes, but it's coming out too quick, which is fine. We'll do this one instead. So dump some in there. So you have the dry ice in there, and the gas will start coming off, and you can see that. Now we can cap this tight, and you can start seeing the bubbles and everything start forming here. And we can actually add a little more soap on that. You can see it, the steam coming out of it. Okay? And you'll see the bubbles forming as it starts forming there. Okay? You can see little jets here and there. Okay? The point is that there's gas coming out of there, and you're going to see lots of bubbles coming out. And you can see like yeah, you can use the towel on that too, yeah. You can see it's actually pushing pretty hard. That looks like, I forgot we switched that to a towel there, yeah. You know what? Try using that on that, see if it works. Sure. Maybe Zach can fix this and we'll see. Nah, this is not happening. That's okay. I don't want to beat a dead horse too much on that. Okay, so the point of that is that the dry ice is liberating all kinds of carbon dioxide. Okay, so what we're going to do now, I will talk a little bit more about carbon dioxide. So, how about it? So what we're going to do is we're going to take a little bit of dry ice and crush it up a little bit. We got the mallet over here? We got the hammer. Oh, there it is. Mallet. Getting close? Okay. Okay, we'll put it on there. So we'll crush it up a little bit. And what we're going to do is we're going to fill a balloon with the carbon dioxide. Hopefully. You never know sometimes. All right. You ready? That's probably enough, actually. Yeah. Got the balloon? Okay. All right. So, ready?
Yep, go ahead.
How about it? All right. And you can see the gas being liberated is being caught by the balloon. Okay, and it's just going in there, and it'll keep on going. Got it?
Yeah, I got it.
So it'll just keep on going, and that's just the gas being liberated. It's being caught. So what is the gas inside there? Carbon dioxide, right? Okay, so what's the molecular weight of carbon dioxide? So it would be 12 plus 16 plus 16, right? So 16 times 2, 32, plus 12? 44? Zach's saying 44. 44? Hey, see, we have confirmation. It is 44, by the way. Okay. So, what's the air again? Just air? Mostly nitrogen, right? No, it's mostly nitrogen. Okay? There is absolutely some oxygen. There's some carbon dioxide, especially up on stage right now with all the CO2. But for the most part, it's nitrogen. So, what I want to do is I want you to blow up a balloon. Yeah, so blow a balloon about that size. Okay, so I once saw a cartoon at one point in time where the character in the cartoon, it was a Calvin Hobbes actually, but the character had a helium balloon and let go. What happened? It went up. And his conclusion on that was gravity is arbitrary. Okay, well, one of these balloons is nitrogen, while the other one is carbon dioxide. Okay, so go in front of the stage there, yeah. Or not in front of the stage, but in there. So what happens if we drop it? Let's find out. Good. So Calvin was right? I mean, gravity's arbitrary. For some reason, gravity's pulling that down forward, right? No, obviously not. Gravity's gravity, right? But what you do know is that carbon dioxide is significantly more mass than regular nitrogen, okay, which is what we're breathing in the air. As a result of that, it will drop faster, okay? And therefore, the carbon dioxide will go down a lot faster and sit lower than other gases. Okay, so you could light up that. Let's see if we can get this thing going, because I like to have the gutter. And Jack still needs about, what, 10 minutes? About that? Okay. So we're still waiting on Jack's thing there. But, yeah, make sure you keep the balloon separate on that one, yeah. So carbon dioxide is heavier than, like I said, heavier than nitrogen. Where are we at anyway? Red lighter. Yeah. Which means, and what other thing we know about carbon dioxide is, that's what I was going to do with this, yeah. So these right here that we have scattered all over the stage, okay? What is the point of this? Putting out fires. What's in them? That's a trick question. It depends. Okay. A lot of these are carbon dioxide. Okay, so it's carbon dioxide in there under pressure. So whenever you pull the pin, it'll spray carbon dioxide everywhere. Now, not everything, because not everything can be put out with carbon dioxide. Okay, but most common fires can. Okay, so you have a gas that is heavier than air that can put out fires. So what we're going to try to do, and we got most of them on this one, we're going to light it up. Go ahead and light it up. Okay, and what we're going to do is we're going to try to put the candles out using the carbon dioxide from these. So I'm going to actually crush up some too to try to get this going pretty well. Where's my glove anyway? Thank you. All right. So in practice on this one, we got to flow, but the wind flow up here is not our friend. So I'm going to generate some carbon dioxide. We're actually going to throw a chunk of carbon dioxide. Will it stick there? It's got to slide down. All right, we'll deal with that later. Okay, so you can see it's coming out pretty good now, right? Would you do the honors up there? Sure. Okay. Yeah, go ahead and get it going pretty well. I'm going to crush up a little bit more just in case. Let's see how many candles we can actually knock out. Because again, the gas is heavy, so it's going to go down. So we actually have these little tea lights in there, and there's a lip on them. So so as the gas is slowing down, we got one, doing good. Come on, do it. Almost there. No. Oh, that one's still hanging on. All right, let's try another batch. All right, let's try one more here. Oh wait, no, it went out.
Yeah, it went out.
It went out. We got it. All right, we actually got them all. Well, I had some extra ice here. So when you come into a fire or something like that, this will absolutely work on most fires, okay? But not all fires. What do you think, Jack? A little bit more, maybe? What's it? How much more time we got? A couple more minutes? All right, so I'm thinking that we try. We might be good on this. Okay, so the trick on this one, so the nitrogen triiodide, the real trick on that is if it is wet, you can't hurt it. If it is dry, everything hurts it. Okay, because when it comes down to it, that structure is actually more explosive than like nitroglycerine. Okay, anything will set it off. So as long as it's dry. And the trick is getting the timing right on it, which is why I'm wondering this. So Jack, how would you like to set it off? Use a stick? We got a science stick? That is the official science stick, by the way, on that one. So, all right, let's see if we go. Let's kill the lights. How we can potentially see this. So we'll see if we see the shock wave on this one. We're not dry yet. Yeah. We got to wait a little longer, yeah. So I'm trying to rush it. I was timing it, but I want to make sure I get it before everyone's there. All right. So what do we have here? Coming close to time. So one thing I do not want to do is get your teachers in trouble by keeping you here longer than you know I'm allowed to. So that's probably another 5 minutes there on that one. That's my guess on that one because it's getting pretty close. We tested the 1 on that, but it's not there yet. Yeah. I'd say we do nitrogen. I'd say we do the magnesium. Yeah. We'll do that one. All right. So I was mentioning about. Leave that a little bit long. If you have to wander off, I am not going to be disappointed in that or anything. I understand that the time constraints, but what we're going to do is we're going to do a simple thing, going along with my path here. Yeah, grab a block, 2 blocks. Was it? Magnesium should be right over here. So, one of the ones that we burned earlier was magnesium. And that was the one that kind of sparklered. Should be back here. Things got shifted around a bit. Is that the one? Yeah. Excellent. Okay. Do we have the torch? Yeah. Yeah, we're done with those, yeah. All right. Where did my tape go? Where did magnesium tape? They're blocks. So we got to set this up a little bit. All right, so you know what? One thing I can do, Jack, look around for the magnesium tape. There's a spool of tape, like magnesium tape, real thin stuff. Yeah. Grab the knife and start giving me shavings. Yeah. All right. So one thing I can do while we're finishing up, because I'm running low on time here, so I don't want to go on too much, but I do want to go through my acknowledgments before it. And if you have time to stick around, we have some liquid nitrogen, and I was going to talk about when waves stop moving as a final piece of it. But again, we're running over time, and I don't want to keep you. But so if you do have that, we have some marshmallows and some cheese puffs if you want to play around with them, because it's good stuff. But if you have to go, you have to go. It's the way it is. I can't stop that. But I do want to go through my acknowledgments as we're setting up for this. So acknowledgments, I would like to acknowledge the SACP, the SSP, and PitCon, especially. They're the ones that funded us on this, and that's the organization that organizations I'm involved with here. I'd also like to acknowledge my family, my wife Sierra and my children, who have not seen me in probably a couple months as I was trying to set everything up and getting everything coordinated for this. Also, Mark Hiles for Stony Lonesome Fabrication Design for the Rubens tube, the gutters. Outside of putting a really good roof on my house a while back, Preferred Contracting Service provided me with some gutters. University of Pittsburgh for supplies and the dry ice and all that good stuff, plus a stage presence here. And also Penn West University, who provided me with some students to work. And then also, of course, thanks from the Kiski Science, and our new developed thing here. So, and obviously, thank you all for coming. It has been a lot of fun. And thank you for the teachers who put a lot of effort in getting you here, because the paperwork involved is probably more staggering than you can imagine on that type of thing. Let me tell you on that. So thank you all for the effort you put into it. And we will try to get you a couple of other things. What do you think? Want to try this one out again, Jack? Yeah. Let's see if we get it. They'd be ashamed not to see that one. All right, let's see it. It's a bit wet. All right, it's going to go off when it goes off. Okay? What will happen eventually is one will set off the next, which will set off the next. It will all go up at once. Okay? But unfortunately, it's that's going to be a work in progress on that, I guess. Where did my magnesium tape go? Do we have a pile yet? Yeah, put a pile together of that. Yeah, I had some ribbon. You see it anywhere? Here's my ribbon. Yeah. Okay. So we do have a ribbon here. We have a block here. We have a second block?
Yeah, right there.
Okay, cool. Let's say. Thanks for coming, guys. Say we have the block. We might as well use it. Like I said, if you have to go, you have to go. All right, dig a hole, if you can, in there. A small hole there. Yeah. I do want to prove that carbon dioxide does not put out every fire. So that is getting a.
There are 2 rings out the desk.
Okay. Quick announcement, there are apparently 2 rings that were lost. If you're missing some rings, check with the soldiers and sailors personnel. We just smash them together, it'd be fine too, right?
Get some blocks.
Yeah. All right, that's taking too long.
Yeah, I guess.
All right, so we got some magnesium going on here within the dry ice. So what we're gonna do is we're gonna set off the dry ice. I'm sorry, set off the magnesium. And what I want to prove to you right on this one is carbon dioxide cannot put out every fire. This will keep on burning. So once we get it started, Noah's going to place the block on there. It is between 2 big chunks of dry ice, all carbon dioxide. Go for it, drop it. It did not put it out. It burned out. We could add more. Yeah, we'll do another one.
Where did you say the rings were again?
Check with the soldiers and sailors, yeah. 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 You can melt a pocket. This is really hard dry ice there. Go for it. Quite low. So Jack got too close to the triiodide. So we got some very, very solid dry ice. It is extremely compact. This is the hardest stuff I think I've ever seen on that. So digging a hole in it, I should have brought a drill. You know, that's what we're seeing here. And by the way, on this, remember, this is not a theatrical thing. I'm a scientist. We're doing science here. Science will work the way science works. And usually if something doesn't work, that means you're forgetting a factor. So you just got to find that factor and you go for it. So we got a bit of a hole there? What's it? Okay. Actually, I should get some magnesium strips. Wow. No, that'll be good. I think that'll be fine. I think we just smashed it there a bit. So we'll add some more magnesium to it. All right. So we got the pile of magnesium. Is that this way? Oh, this way. Gotcha. Yep, I'm with you. All right. All right, let's see if we can do this again. So put it on as soon as you see it light. All right, do it. Put it on. You can see it's going inside there. There it goes. All right. So thank you all for coming. If you'd like to come and speak with us or anything, feel free to come up to the stage. And I do have the liquid nitrogen sitting here.